Okay, so this is on your review assignment number 2. This is question number 4, Chem 30. And this is a stoichiometry question. So remember stoichiometry, when you hear that word, that is the relationship between amounts of substances in a chemical reaction. And oftentimes what we're going to have to do is create an equation, balance it, and then do some conversions to moles. Use that balanced equation to go from moles of this to moles of something else in the equation, and then we'll probably have to convert back either to grams or to liters or to representative particles of some sort. So let's go through this one. Number 4, okay, you ready to write this one down if you haven't started this yet? I'll give you a hand with this one. So if it says this, if 14 moles of butane, and it gives you the formula there, is burned, then A says calculate the number of moles of oxygen gas required. Okay. So again, stoichiometry needs a balanced chemical equation. So I've got butane and oxygen gas combining. So I'm going to start with C4H10, butane, combining with oxygen. And of course, oxygen gas is always O2, one of the diatomic 7. And I should recognize this as a specific type of reaction. Remember the types of reactions? Which type of reaction is this one? Anybody remember? Combustion reaction. That's totally correct. A hydrocarbon combining with oxygen is a combustion reaction, and we always know that the products are carbon dioxide, so some carbon from here, the oxygen from here, that's going to connect, and what? Water. Very good. So this is sort of the skeleton equation, and now I want to balance it. So I look at my carbons. Right away I notice a problem that I have 4 carbons over here and only 1 over here. So the first step might be to put a 4 right there. That's going to balance the carbons. All right. Now what about the I'm going to leave the oxygens for the end because I just have oxygen in one spot. So I'm going to do the hydrogens now. I have 10 hydrogens on the left side. I only have 2 here, so I think a quick little 5 right here would be appropriate. Now remember, you only put coefficients, not subscripts. You never change, the subscript here. You don't do that because that changes the entire nature of this chemical. So you can only use multiples of moles, okay? All right, so carbons are balanced, hydrogens are balanced. Now we look at the O's and see what happens. I've got 8 oxygens in this compound on the right, and I've got 5 over here. So what's 8 plus 5? Is 13. Okay, well 13 is an odd number. That's a bit sad. How am I going to get 13 from here? A little trick is any number that you need, if you need to multiply by 2, just put that number over 2. And when you multiply this, those 2's kind of cancel out. You're left with 13 here. Now the only problem is that we don't like fractions or decimals as coefficients in our chemical equations, right? Let's do whole number ratios. So the easy thing now you do is you multiply everything by 2. So I'm going to make this 1, a 2. I'm going to make this 13 over 2, just a plain old 13. I'm going to make this an 8. And I'm going to make this a 10. So let's see. Now we have whole number ratios, and everything should be balanced. Let's just do a quick check here. So 8 carbons, 20 hydrogens, and 10 times 2 is 20 hydrogens. And we have 26 oxygens, and we have 16 and 10, 26 oxygens. That's balanced. Okay, we good to go there? That's a little review of balancing there. That one's for free. Okay, so let's get into the question here. So I've got 14 moles of butane. Hey, this is great. We're not given grams or liters or particles. We're given moles. So we can kind of like all of a sudden just jump right down to moles here of butane. That's 14.0. Look at that. So now what we do is we find the number of moles of oxygen gas required. So this is where we have to do a little conversion here to moles of O2, right? And how do I find the moles of O2? Well, the ratio is 2 to 13. So this is 13 over 2 times as big, right? Or times as many moles. So what you do is you always take the coefficient of the substance you're converting to, put that on top. And then the coefficient of the substance you're coming from is on the bottom. Okay? Okay, write this down. Yeah, you can do it. Yeah, follow along here. Okay, so when we do that, let's get our calculator out. Question, yeah?
So why wouldn't we put 13 instead of 13 over 2?
Why wouldn't you just use 13?
Yeah.
Well, because this isn't a 1 here. Do you see how going from 2 to 13, I wouldn't multiply 2 times 13 to get 13?
Okay.
Yeah. So it's a ratio. So look at this, 2 to 13. That's the ratio of the moles of these two substances in this. So this is like a 2, and this one's going to be like the 13. Okay? So you would multiply this by 13 over 2, which is 6.5. So 2 times 6.5 gives us 13. So that means that 14 times 6.5 should give us the actual number of moles we have. Does that make sense?
Yeah.
Yeah. So always remember to put this one underneath here, and then that's all you need to remember. You should be good. So where was I here? Okay, so 14, I'm going to go times 13 divided by 2. And that'll give me 91. All right. So this is 91 moles right here of O2. So calculate the number of moles of oxygen gas required. A is 91 moles. Okay, any questions there? Yes.
Just for combustion in general,
Mm-hmm.
if it's creating, does it create water? Yeah, it
Yep.
creates water
Yep.
afterwards, so why wouldn't it put itself out? Like, how wouldn't that put itself out?
Okay, it always creates carbon dioxide and water. Okay, and so why wouldn't it put itself out?
Yeah.
Okay, that's a good question. It's not like it's when you're burning a hydrocarbon. Okay, the products are released either as moisture, could be. It's not like it's a bucket of water that all of a sudden that gets produced and it puts itself out. No, wouldn't be like that. You would produce that carbon dioxide gas, and then water would be a production. It would come out of that. It wouldn't put itself out. That's a good question, though. No one's ever asked that question, I don't think. 21 years of teaching, I don't think I've ever got that question. So yeah, so water is produced, but it's not like it's a bucket of water that douses itself. Okay? So B, calculate the number of moles of carbon dioxide produced. Okay, so we're still in moles, no big deal. So if we've got, now we could use either one of these moles that we have now to convert now to carbon dioxide. So for B, maybe I'm going to go from this one to this one, because it's just a simple times 4, right? Just times 4. So that means that I can do 14, right, times 8 over 2, or times 4, to get moles of CO2. So 14 times 4, what's that? 40, 56. 56 moles. And so B is 56 moles of CO2. So this one's pretty easy because we didn't start with grams or anything like that. So there's some calculations that we didn't have to do with this one. So this one's kind of nice. If you're just given moles, you can start right here on this row. You don't have to start from grams or anything and convert first, right? But for C, what we do notice here is that this C question is asking us about the mass of water produced. So now we have to consider water as well. So you can go from this number of moles here to water moles, or you can go from this number of moles to water, or this number of moles to water. You can start anywhere you want now. I'm going to start with the 14, like we kind of have been the entire question. So what we need to do now is find the moles first of water, and then convert to mass. Because remember, these numbers here are ratios of moles. So these are moles. So I need to go from moles to moles first. So 2 times what gives me 10? Times
20.
Well, okay, 10 times 2 is 20, but 2 times 5 is 10. So what that means is I need to go 14 moles times 10 over 2, right? 10 over 2, or times 5, to get the number of moles of water. So what's 14 times 5? That's going to be 70. So we have 70 moles of water involved in this reaction, and I need to now convert to grams. So when we go from moles to grams, what do we do? Times grams per mole. So what's the grams per mole of water? Well, grams per mole of water is going to be 2 times the mass on the periodic table of hydrogen plus the mass on the periodic table of oxygen. That's going to be about 18.016 or something like that, okay? We can do that, use that exact number on your calculator. And then we're going to multiply this by the 70. Okay? So, let's clear that up. So 70 times, and then 18.16 is pretty close there, but let's do it exactly here. 2 times 1.00794 plus 15.9994, and I get some kind of error. 1, 2, 1, 2, 3. Okay, I got one too many brackets, looks like. Let's try that. 1261, 1,261 grams. 0.090696. And then for sig figs there, for sig figs, what do we got for sig figs? Well, we only had 3 significant figures in our original measurements, so we should probably just go with 3 sig figs here, which is just the first 3 numbers with this third number being rounded. So 1, 2, 6, and I do have to put that placeholder there. So 1,260 grams of H2O, and we'll just check that number here. Okay, so another way to write that, as I mentioned, 1.26 times 10 to the 3 grams of water. So that's number 4. Oh, and we also did add for A and B proper sig figs, 91.0 really should be the proper answer, and 56.0 in keeping with the significant figures of the question. Okay, you guys are good on this one? Awesome.